Yeah, hi everyone. Thank you all for joining us and welcome for our fourth installment now of the webinar series for the STFC network and batteries and electrochemical devices. So first things, some house rules. So there's a poll that I've just launched. If you guys could answer the questions, it's anonymous. It would be really helpful for us. And then throughout the presentation, you can all type your questions in the Q&A box. And then also, yeah, this session will be recorded. Today we have a panel to ask the questions again, so it's not just me. We have Pablo and Garcia-Salaberri, the assistant professor at the University Carlos III of Madrid. Hi, Pablo. And we also have Hamish Reid, who's a PhD student at UCL. And then, of course, we have our speaker today, who's Dr. Jervis. So yeah, Rhod graduated from Balliol College, Oxford in chemistry in 2008. And after a time working for a medical research spin-out in his hometown of Swansea, he obtained his PhD in fuel cell catalysis from UCL in 2015. And then after a postdoctoral research position, which he did in redox flow batteries, he took up a position as a lecturer in chemical engineering in 2018. He is currently also the project lead for the Faraday Institution Fast Start project on lithium-ion battery degradation. His research interests focus on studying energy materials using a combination of electrochemical and X-ray techniques. And some of you may know Rhod used to be the manager of this STFC network. So yeah, welcome back as a speaker now. And yeah, now I'll give the floor to Rhod. So whenever you're ready, Rhod, please.
Thank you, Rema. It's in better hands now, I think. Yeah, thanks for the great introduction, Rema. That actually sort of covers a little bit of my background, which I'm going to talk about today before I get into the science. As I think it's technically the early career meeting, these sessions, right? So it's to give some perspective on how I got here and how it's been going so far. The bulk of the science part of the talk is going to be about how we can apply X-ray computed tomography, which is a 3D imaging technique, to redox flow battery electrodes and other similar materials. And a lot of this work is work done in very close collaboration with Matt Koch and Jeff Gostick. At the time, Matt was in Jeff's group in Canada and is now actually doing a postdoc in the EIL, which is where I and Rema and lots of other people work. But there's also some work that we've been doing with collaborators at Queen Mary, Anna Jorge Sabrido, and Magda Titerici, now in Imperial, looking at these sorts of materials, how to modify them and improve their chemistry, as well as their sort of flow characteristics, and also use in other fields like fuel cells and supercapacitors. So I'll get onto that in a little bit. Working? Okay. But yeah, I want to talk a little bit about my background and about how I got here as well. I don't know how useful it will be because, as you'll see, it's sort of a little bit random, but hopefully it'll give you a data point anyway to think about if a career in academia is something you're interested in. And I'll sort of talk a little bit about how it's been going so far, just past my second anniversary of being an independent academic. Then I'll talk a bit about the broader lab group which I work in, which is sort of comprised of most of those people you see in that photo. Is probably about close to 80 people currently, and 5 academics within that group. So that's sort of a bit different perhaps to some other starts of academic careers, and I'll sort of talk a bit about how that is. And then I'll go into, as I say, the science of the talk, so I'll skip through that. Okay, so I was born in Swansea, as Rema said. This is actually the home of the fuel cell. I don't know, can you see my mouse there? Yeah, that's William Grove, who invented the concept behind the fuel cell, at least, way back before the combustion engine, actually. And so I guess I had fuel cells in my blood a little bit. That's me when I was a little baby. And this, believe it or not, is actually Swansea. It's a very beautiful part of the world when the sun's shining for the week in June that it happens. But if you've not visited there, I'd recommend it. It's very nice. I then went on to do an undergrad in chemistry in Oxford. I chose chemistry not because of some incredible love for chemistry, but because I liked science in general. My dad, who's also pictured there, was a civil engineer, and so he was very good at physics and maths and these sorts of things, but he hadn't really done much chemistry. And so I thought, well, if I'm good at chemistry, then that's probably me being good at chemistry rather than my dad being able to help me. So maybe I should do chemistry. Wasn't particularly well thought out. I also nearly didn't go to Oxford because I thought it would be, you know, as everyone thinks it is, a bit stuffy and a bit perhaps not the kind of place that I would fit in very well. Turned out to be quite wrong about that. But I went in the end because I thought I'd be a bit daft to turn it down. Actually, I had a very good time there. There's a picture of me and some of my chemistry colleagues finishing our exams. A weird sort of tradition in Oxford where they trash you at the end of your exams. Your friends come and throw a load of crap all over you in celebration of the finishing of your exams. The way the chemistry degree works in Oxford is you do sort of 3 years of lectures and exams, and then you do a 1-year master's thesis at the end. So it's a bit like a sort of 1-year PhD. You're embedded in a research group and you do some research and produce a thesis. And that was great fun, and you get exposed to some real science. But the process of writing that thesis, I was quite sort of exhausted by the end of that, and I was like, I'm never doing that again. I don't understand how people do that for 4 years for a PhD. No way. So I then went back to Swansea. I'd been working in my summers for this company, this startup company called Hamish, spun out from Swansea University in the chemical engineering department, and they were trying to make an artificial lung as a sort of blood-air mass exchanger device. So I'd been working for them in the summers for a couple of years while at undergrad, and I went back to work for them, and that turned into a sort of 9 or 12 month stint, I think, working for them, which was quite interesting. But I knew that I was really more interested in energy, particularly renewable energy, and having some input into sort of the climate crisis and sort of dwindling reserves and move towards sort of electrification of everything. I also wanted to go traveling for a bit, so I quit that job, went traveling, had to think about what I wanted to do. By that point, I'd realized that most people in research have PhDs, and that actually a PhD is not some unobtainable thing that only geniuses can achieve. I met quite a few people in Swansea who had PhDs, and I thought I could probably do that. So then I decided a PhD was the way to go, and obviously I wanted to go into the energy sector. And a lot of my friends had moved to London in the 2 years that I'd been back in Swansea and traveling. And so I decided to do a PhD in London. I had a bit of a search and found the UCL Energy Institute, and they said they were taking applications for PhDs in a couple of months' time. So I thought, great, I'll do that. When I applied, it was kind of odd. You had to propose your own research question. And I thought, you know, this is it's a bit strange. Often you get told what to do broadly, and then you sort of diverge off there. So I sort of came up with some project based on fast charging electric vehicles or something. Went to the interview, and it quickly became clear that we'd both got the wrong end of the stick. I think this is quite a new program for the institute, and they were largely looking for people to do things like model energy efficiency of buildings and things, which was not really my thing at all. So about halfway through the interview, I think we both said, yeah, this isn't this isn't what you want to be doing, is it? And I said no. And I'd happened to have Googled a little bit more about UCL, and Dan Brett's name came up in relation to research of batteries and fuel cells and things like that. And so I said, you know, do you do more traditional lab-based PhD things? For example, do you work with people like Dan Brett? And they said, no, but we know him, and we'll pass your name on. And I thought, okay, whatever. Went back home, felt a bit dejected that I'd been waiting around for this sort of opportunity that wasn't exactly what I wanted to do. And a couple of days later, I get a phone call from Dan in his big booming Essex voice saying, here, you want to do a PhD with us? Come down to London. Like, okay, great. Came to London and met Dan and saw what he was doing there, and really, you know, liked the idea of the project. Dan seemed to like me, which is good. You never know what on your CV people are going to pick up, but he seemed particularly interested in the fact that I was a darts captain at university. So yeah, those things sometimes are important on your CV. So he offered me a PhD in fuel cells. At that point, I think Dan had been at UCL for maybe just a couple of years. So it's quite a small group, and it didn't have a huge amount of facilities, but it was still a really good place to work, and I enjoyed that immensely. So much so I decided to stay there for a postdoc. This time changing to flow batteries, which I'll talk a lot more about in a second. And that postdoc was on a collaborative project with Imperial College and Dalian Institute of Chemical Physics in China, which actually has one of the biggest sort of research redox flow battery companies in it there. As Rema said, I also did the sort of administration of this STFC network during this time at some point. And then in 2018, I took up the role of what we call the project lead. So basically the scientific administration of the Faraday degradation project, which is run by Claire Gray at Cambridge. Initially, I was doing that on my own for a year or so, and now Dave Hall is giving me lots of help on that, which is great. So it's a sort of shared role. And sometime shortly after that, I got my academic position in June 2018. And so, yeah, so balancing that sort of what was supposed to be a full-time role in the Faraday degradation project with then becoming a lecturer was quite tricky, and I'll talk a bit about that later. So, as I said, there was a lot of this was by accident. You know, Dan happened to call me and offer me a PhD. I didn't necessarily think about what degree I wanted to do particularly closely or any of these kind of things, and so this is probably not a great example of how to get a career in science. But I think it is quite important to, although you have plans and ambition, but to understand that things might change and you have to sort of adapt and go with the flow, and hopefully things work out well. Another key thing is collaboration. So I'll talk a lot about some of my collaborations in this work today, and a lot of it was, you know, a lot of them have been very fruitful. Some of them have led to further collaborations. I mean, Pablo, who's on the line at the moment, for example, I was introduced to by Jeff Gostick, and we've had some successful work together as well already, and hopefully more to come. I think it's quite important to diversify in the science that you're doing. So I've looked at lots of different areas of electrochemical technology, from sort of synthesis of materials up to a bit of modeling. I'm not exactly a modeler, and Matt has done most of the modeling in this talk today, but I've at least sort of had a brush with it now. So diversifying is quite good. Saying yes to lots of things, lots of talks, lots of other stuff, even just helping people out is usually a good thing. It gets your name out there. It means that people know who you are. When it comes to applying for jobs, that's quite helpful. But if you say yes to everything, you'll end up burnt out. So I think one thing I've learned in the first couple of years of the academic position is to try and say no to some things. But varying your experience is important as well. So obviously the quality of your science and number of your papers is hugely important, but it's not the only thing. Particularly now, teaching is getting a lot more focus, and if you can demonstrate some teaching experience, that's a really good thing for an academic position. Obviously, also it's good for you to understand if you enjoy that, because it is a key part of what most academics do. I got some management experience with the STFC role, which then led to a sort of bigger management role with the degradation project. It's quite a large consortium project, and that sort of showed that you have the ability to sort of manage larger projects, which is obviously very important as you become an academic. I did a lot of outreach activities as well. That picture there is of UCell, which is a group of, still going very strongly actually, group of PhD students and postdocs in our group, and slightly wider than our group now, do outreach events, teaching the public about fuel cells and electrochemistry in general. But also getting to know other areas of science. So collaborating and helping out with other experiments. This is a picture on the bottom of Donal, the previous PhD student, and his sort of supervisor from NASA, Eric Darcy. And we had a series of experiments there led by Paul Turing and Eric into thermal runaway batteries, which I helped out with Donal for quite a while, and that gave me exposure to batteries. And then I've ended up sort of in that field a little bit as well. And so, you know, varying your scientific involvement can be quite useful as well. But the main thing I think is get to know the community. I think that the STFC really highlights this, but the UK community is really great bunch of people doing good science. And the more you get to know everyone, it's actually quite a small, tight-knit community as well. The more you get to know people, the better for your career, and just because it's fun as well. It's nice. So 2 years in, what's it been like? It's very hard work. A lot of this is to do with the fact that you're pulled in lots of different directions. So I said you have to be multi-skilled there. I mean, you end up being not just a scientist, but a manager, a accountant, a advocate, maybe a bit of a politician. You end up being a teacher. You end up doing a lot of admin as well. So you've got all of these different roles that you have to balance, and always trying to keep your science being the most important thing if that's what you're interested in doing. So it's quite difficult in that respect to pick the right things to focus on. So for that reason, you really have to like it, I think. The other thing is you have a lot of responsibility. So if you go straight from a postdoc to an academic position without any of these other things I talked about, where you have a bit more responsibility or maybe a bit more management, etc., it can be quite a shock, I think. You suddenly are responsible for, you know, for the pastoral care and the scientific care of PhD students, and that's quite a big change, I think I've found anyway. also this 2 years have gone very, very quickly. So if you look back, I look back at what it was like 2 years ago and what I was like 2 years ago, and it's, it's gone very quickly, and I've sort of, I think, adapted quite well to these sort of new responsibilities and workloads as well. But it is, it is quite a shock, and I think that the number of other things I did, so I should say I managed to get a bit of teaching experience as well before this position. So all of these things just knock the edge off that jump. It's still a big jump, but because I've done bits of it before and I had experience a little bit, then that helped with that a lot. So I find as well so far that being nice and friendly with the community is much more useful than being hyper competitive. That might change as I get to be an older academic and everyone's sort of being really, really ambitious and competitive. But for now, it's stood me in much better stead than sort of being hyper competitive or ambitious. So yeah, so that's me. If there's any burning questions on how I got here, then I'm happy to answer them. But as I say, I'm not sure it's necessarily a model to follow, and I'm appreciative that I've been very lucky. So yeah, that's just to sort of give you a perspective. One thing I should say, of course, is I did my PhD postdoc and now work in the EIL in the same lab. And a lot of people would advise against that. And I do understand that. And I think that traveling to other groups is great for various different reasons for, when you move around for jobs. But for me, I think that as I say, when I started my PhD there, the lab was quite small, and Dan and then later Paul, when he joined, were very successful in obtaining funding and getting lots of different equipment. And so I felt that the lab was growing as I was trying to grow my career as well, and also diversifying in different areas of science. So I thought actually it was probably the best place to continue my science, and it's just a good group of people that I want to continue working with as well. So if there are no questions on that, I'll skip on forward and I can answer them at the end maybe. Yeah, so as I say, the Electrochemical Innovation Lab based in UCL. This slide is now out of date. As I say, there's about 75 of us probably. And 2 years ago, the directors of the EIL, Professors Dan, Brett and Paul Shearing, I had 3 lecturers, me, Tom and Alex. And so we've sort of grown the group in that respect. So it's quite, well, it's not unusual, I suppose, but it is sometimes, it's a different thing to start your career in an established and well-funded group. It's most of the time that's really, really helpful. That's great. I guess there's a bit of difficulty in sort of making sure that you have your own niche within that, and that you're, and that you have your own independent career. But for me, that's been great because Dan and Paul are very supportive, and I can sort of obviously do what I want, which is great. And then, yeah, being part of the larger team, I find much better because I enjoy collaborative work. And we cover a huge range of sort of electrochemical technologies, right from low technology readiness levels up to sort of spin-outs, and there's a few details of spin-outs from our group that we can discuss later if needs be. I'll skip the complex a little bit, but just to say that, as I say, we've been quite successful in receiving funding, particularly through the Faraday Challenge and Faraday Institution, which I'm quite closely involved in. And I think actually my involvement in the Faraday Institution in the degradation project probably was a key part of me being able to secure my academic position as well. A lot of the work that we do in the EIL is about understanding and diagnosing different electrochemical systems. So I'll talk a lot about redox flow batteries today, which is on the left, but also we obviously look at lithium-ion batteries. This is an example of lithium sulfur battery here, electrolyzers, solid oxide fuel cells, PEM fuel cells. It's about understanding how they behave under different conditions, and a lot of the time using operando techniques, particularly X-ray techniques, X-ray imaging in particular, to see how these devices work and how they change under different conditions. So I'll give a bit of a background about tomography because it will form quite a bit of this talk, I guess. It's an imaging technique similar to a CT scan in medical imaging, where essentially you are looking at an absorption image of a sample of the absorption of the X-rays. You rotate your sample through 180 or 360 degrees, and using some algorithms, you turn a series of 2D projections at different angles into a reconstructed 3D volume. And this has the particular benefit of being non-destructive, of being quite versatile in terms of the types of materials you can study. And it means you can, because it's non-destructive, you can do operando measurements, and you can also do measurements on samples that you then, put back inside a battery, for example. So you can see how things are evolving, which is sometimes termed sort of 4D tomography because you've got that time dimension in there as well. And there's a wide variety of resolutions of spatial resolution and time resolution as well. So in the lab, we're lucky to have quite a good suite of tools here. We've got sort of Microtomography, Micro CT, which I'll talk about today, and Nano CT, so-called Nano CT with the Versa and the Ultra machines here. And then obviously you can go down to higher resolutions with things like Fibre SEM and Nano Fib machines as well. I'll largely talk about micro and nano CT today, but there's always a trade-off between the resolution and the sample size that you are studying. So if you want to study a big thing, you often can't get particularly high resolution. There are some ways around that, which we'll talk about later. And the good thing about having the lab equipment, of course, is that we've got lots of access to it, and we can take lots of measurements as well. However, obviously, a lot of this can be done at synchrotrons, such as Diamond or the ESRF in Grenoble. And this combines the ability of high spatial resolution with often very high temporal resolution as well. So you can see that the lab instruments actually achieve some very high resolutions compared, comparable with synchrotrons, but the synchrotrons are just much quicker in acquiring the data. And the ESRF has recently just come out with an upgrade as well, so the flux is even higher, and so we should be pushing down to much quicker acquisitions. So there's some exciting things to be done with that, with these new generation of synchrotrons, I think. Okay, yeah, so as I say, there's our lab machines there, the Versa, the Micro CT, and the Ultra, the Nano CT. So redox flow batteries. Redox flow batteries are sort of a hybrid between a battery and a fuel cell, in that they have a sort of central device that's akin to a fuel cell that does the conversion, does the charging and discharging of the cell, and they have a sort of a sealed system containing the total charge of the battery. So in this case, this is a vanadium redox flow battery, and you have some tanks of vanadium 4 and 5 and vanadium 2 and 3 that have obviously a certain capacity. But the good thing about the flow batteries compared to lithium-ion batteries, for example, is that capacity can be tweaked just simply by adding a larger tank. So you've got more electrolyte, you've got more energy capacity. You've got a higher power, you can just design a bigger cell in the middle so that you can convert more of it, charge more of it per second. And so this is really good. It gives a lot of design flexibility. There's a lot of flexibility in chemistry as well. The vanadium chemistry is sort of the most widely established in terms of the industry, but the high cost of vanadium is meaning that people need to look away from this now a little bit. One of the key benefits of the vanadium technology is, of course, you've got vanadium species on both sides. Crossover between the two electrolytes is actually a bit of a problem. When it happens in vanadium, at least you're just putting vanadium into vanadium, and so you can electrochemically regenerate the cell. Whereas if you were crossing over zinc or something, then you'd actually end up poisoning the cell. So say you've got two redox couples contained in two separate tanks. They flow into a device that does charge transfer, the charging and discharging, and because of that, you're decoupling the energy and the power of the system, so they're really quite flexible. And all this means, and I should say that most of the time they have quite low energy densities compared to lithium-ion batteries, for example. So we're talking firmly grid-scale energy storage solutions here. You can see an example of, this should be updated as well. Now Red T have merged with another company, or been bought by another company. But there's an example of a sort of shipping container unit of the flow battery there. And one of the biggest companies, Ronke Power, also build these things to be shipping container size. So you've got these modules of shipping containers. Of course, because you're flowing electrolyte, you need to use porous media in flow batteries. And there's a variety of different porous media that gets used. Carbon papers, which are similar to the gas diffusion layers in fuel cells, are used quite a lot. And also carbon felts, which are a bit more of a sort of 3D woven structure, normally woven polymers that are then carbonized into conductive carbons. So these porous media have to have a high surface area, so we can have lots of reaction taking place at any particular time. They've got to have good electrical conductivity, so we can charge and discharge efficiently. They should have good wettability for the electrolyte that you're using as well, so that you utilize the whole volume of the electrode. And of course, they've got to be porous and also highly permeable, because when you're pumping the electrolyte through these materials, if you have low permeability, you're going to have a larger amount of parasitic pumping losses. So you actually use a lot of your power in pumping the electrolytes around. In the case of aqueous electrolytes as well, it's quite important on the negative electrode to suppress the hydrogen evolution reaction. which is a bit of a problem in vanadium flow batteries. If you go to too negative voltages on the negative electrode, then you're going to start to split some of the water into hydrogen, and that leads to capacity fade and other problems in the flow battery as well. So this is why they're quite often just carbon felts, and they're not decorated with highly active metals like platinum, for example, because that would just catalyze the HER. So there's a lot of work going on to try and find things that will catalyze the vanadium reaction, but not cause hydrogen evolution. So we've used X-ray CT to study these materials. They're sort of ideal, they're porous, they're about the right length scale for what X-ray CT can study. And we've done it in a variety of ways. We've got this sort of operando flow cell here where we can image the electrodes during flow and during charge and discharge. A lot of our studies actually found that the carbon electrodes are relatively stable over lots of charging regimes, and so we had hoped to just study a lot of degradation of these materials, but we didn't see a huge amount in a lot of what we've done. Nevertheless, you can see the flow characteristics, which is quite cool. You can also study these materials under compression and see how the various how the materials behave under compression, which can then sort of illuminate the electrochemical results a little bit, again compared with some modeling as well. I want to talk more about some sort of more bespoke electrodes via a technique called electrospinning. Again, a lot of this work is in collaboration with Jeff Gostick and Matt Koch, who made a lot of these materials. But it's a technique that's used quite widely by lots of groups and for lots of different reasons. And it's quite good for flow battery electrodes. It's the basics of the technique is you have a polymer that is slowly extruded out of a needle. The needle is charged, and you have some sort of collecting plate that's also charged, and there's a large bias voltage, normally over 10,000 volts, in between them. And this draws out the polymer into a sort of cone, and eventually it sort of shoots the polymer onto the target. You get this spinning process. You can see in this animation that it's kind of quite random. However, there are things you can do to tune and control the microstructure and the properties of these things. So you can tune the porosity, the fiber size, the morphology, even the alignment. I'll talk a bit about that in a second. And then once you've spun these polymers, you then carbonize them to give you a conductive electrode, freestanding electrode as well. And the properties of the material are sort of very strongly coupled to the microstructure, as is often the case in electrochemical devices. Okay, so I'll start off with a bit of microtomography on these materials. So first of all, Matt made these electrospun materials. There's actually quite large fibers for electrospinning. I should say electrospinning normally produces fibers just less than a micron, which of course increases the surface area for these electrodes, which is great, but it can have consequences on the permeability of the mats as well. Anyway, these included quite a lot of large fibers above 1 micron, and this is spun from polyacrynyl nitride, which is quite a sort of typical material, typical polymer for these carbon felts. But in this case, he rastered across a rotating drum target, and so in doing that, you can increase the rotational speed and bring some isotropy into the direction of the fibers. Okay, so in the X and Y direction, normally you wouldn't have any difference. They're kind of randomly aligned, but if you rotate fast enough, you can force an alignment into that direction. You do, however, get some heterogeneity through the thickness of the mat, because the fibers are put down in time, and that is the equivalent of thickness. And so often 2D characterization misses, you can see an SEM there, sometimes misses the heterogeneity in these materials. And in this case, that was definitely what happened. This is an example of a tomography slice through the material. You can see there's a wide variety of fiber sizes and void sizes around these fibers as well. And also the material looks quite different if you take cross sections through the different parts of the thickness. Of course, with SEM, you'd only see either one side of this, and so you could miss some of those things. Here we've analyzed 2 different materials with different weight percentages, which give different characteristics. And one of the best things about computed tomography is, of course, you get this virtual volume that can be used for a variety of different modeling approaches in the computer very easily. And so one of the things that we did was look at the local fiber diameter using a technique called local thickness, where this essentially sort of assigns every voxel a value for the size of a sphere that can fit within that phase. Okay, so you draw a bunch of spheres within the fiber, and then every voxel that is within a sphere of a certain size has that value. so you can get an idea of fiber size. And if we look at the fiber size in 3 different directions here, so the red one is through the thickness of the electrode, and the grey and blue is in the X and Y plane. As I said, there shouldn't be much variation there, and as you see, we don't get much variation there. On carbonizing, which is the graphs on the right, this 12 weight % one actually had quite a variety of fiber sizes through the thickness on carbonization, and that could be because of contact between plates during this process. You can see for the 13 weight % one, there was actually quite a decrease in fiber size through the thickness of the electrode. Remember that the fibers are being placed on top of each other over time, and so actually this can change the voltage properties because you're spinning an insulator initially, and so that can change how things work in terms of the deposition of these materials. So you've got this gradient through the material, which sort of is maintained during carbonization as well. So you can see there's quite a lot of heterogeneity in these materials already. We can also use the same method as we did for the fiber size to look at I'm going to call it the void size rather than pore, because we'll talk about supercaps a little bit later and have sort of slightly different definitions of pores. But the voids, so the very large pores essentially in these materials, we can look at them in 3D, which is great. We can get a 3D estimation of the pore sizes and the pore size distribution, quite importantly as well. This is a simulation of an experiment called the mercury intrusion porosimetry, which is, as it sounds, you put mercury into the sample under various different pressure, and that gives you an idea of the pore size and the pore size distribution by modeling this. But of course, we don't need to model that experiment of the intrusion of mercury. You can just look at the location of the pores, and you get quite a different view when you do this. So the one on the right is the pore size distribution, just sort of inherently in the material, and because we're simulating this intrusion here, you actually get some blocking or restriction in the channels, so the mercury doesn't see some of the pores that actually are quite large because of blocking of those pores sort of further upstream, as it were. And obviously, if you think about the way a flow battery works and you're putting this electrolyte through the electrodes, that's going to have consequences on the operation of the flow batteries. So we can look at the porosity as well. Again, going slice by slice, if you look at the red one, there's quite a variation in porosity. The porosity is obviously linked to the permeability and other mass transport factors through the electrodes. So you're going to imagine you're going to get a lot of heterogeneities in these materials, which could affect the performance of the flow battery quite a lot. So what Matt did, what you can do with these materials, is to sort of simulate the flow using the method called the Lattice-Boltzmann method. And this sort of applies a pressure-driven simulated flow based on sort of a collision physics. And with this way, you can look at velocity fields. You get a velocity field out of the data, which tells you the fluid velocity at different locations within the sample. So you can look at the effect of the local heterogeneities and porosities on the fluid flow, and therefore you can work out the permeability as well. Okay, so you can calculate the permeability with that. These permeability values, sorry, I should go back. They match experimental values taken on these materials, which is nice. But you can also get a sort of contribution to a local distribution of contribution to permeability. It's technically not permeability because that's a continuum sort of property, but you can look at which areas of the electrode are contributing strongly or weakly to high or low permeability. And so this is what this image on the left is. You can see areas of high velocity, fluid velocity, with this simulation within the flow battery. As you might expect, it sort of broadly follows the porosity of the sample. The porosity here is in red, and you can see the permeability is broadly following that. There are some areas where that's not true, though. You can see on the right is just a distance transform, so basically the size of the pores. And you can see, even though there are some large pores in some areas, you don't get high fluid velocity in these areas, because what happens is when you have these large amounts of heterogeneities in these materials, you end up channeling a lot of the flow. And so you can see in this case, a lot of this flow is sort of channeled through the bottom and the top of the material there. So it's not quite the sort of one-to-one relationship there. and you end up getting pockets of low or stagnant flow. Of course, for a real redox flow battery operation, this would have huge consequences because you'd have very varied overpotentials across your electrode, and then you could actually lead to, as I said, things like the hydrogen evolution reaction being favoured by a large negative overpotential, for example. So the porosity doesn't fully correlate to the velocity of the flow through the electrode is the take home from that. So Matt then went away and sort of improved the electrospinning process and made much more consistent fibers. You can see on the left is what the material I've just been talking about. There's an example of a very large fiber there cutting through some of the smaller fibers. Then made a material that has much more consistent fibers, but smaller fibers as well. And also with this material, introduced some element of alignment by rotating this drum a lot faster. So you can see a lot of the fibers are sort of aligned in this direction here. And so because of this, because of the smaller fibers, and also because we have a much more consistent material, which is sort of verified with microtomography, we can actually use nanotomography now to get a much better resolution of these fibers, but also know that we're likely going to have a representative volume because of the consistency of the materials. So as I say, you always get a trade-off between the sample volume and the resolution. So going to higher resolution in this case means we've got a much smaller sample volume. And actually what we've had to do is sort of laser down these pillars of about 80 to 100 microns, and then use the nanotomography at a much lower X-ray energy to pick out the carbon fibers, and also using a technique called phase contrast imaging as well to pick out the boundaries between these fibers. You can see on the left here one of these original sort of inhomogeneous electrodes, and this large fiber here and the effect that has on a sort of surrounding void. In 3D perhaps it's a bit clearer. You've got this big channel through there via which a lot of electrolyte might flow, for example. And you can see the middle material is quite consistent, but random alignment, and then you've got this aligned material here. The aligned materials tend to delaminate a little bit more because they don't have sort of good enough sort of overlay of fibers on top of each other to keep the materials together, so they're a bit more tricky to work with. But of course, we can do simulations including tortuosity, using tau factor, Sam Cooper's plugin for MATLAB, which is great. And basically, we can just characterize all of these things. Okay, so obviously the tortuosity in this case very much depends on the alignment. If you're aligned with that hole, as it were, you can sort of get a much lower tortuosity. If you're against that big fiber, then you've got a large tortuosity to go around that way. So we made subvolumes there and looked at the tortuosity, porosity, etc. You can see as well quite nicely that that there's some alignment in these materials through this method. Again, I'd skip this, but we can look at the pore and the fiber size. Obviously, but much smaller fibers and much smaller pores in this case, but sort of decent distributions. You can see in the aligned case, you sort of skew towards a larger pore radius because you've elongated some of these pores. To characterize that a little better, Matt came up with a method of defining chords. So this is drawing straight lines in a particular phase, so either the solid phase for the fibers or the void space for the pores, and you draw them in the X, Y, and Z direction and see what is the longest chord you can draw at different locations in that phase. And that gives you an idea of alignment and an idea of fiber size. So for example, if you think about going through the thickness of these electrospun materials, because even though you might have random arrangement in the XY plane, if the fibers are all similar size through Z, you get a lot of chords of the same sort of size. So you get a much sort of, you get a much sharper peak, basically. And so also for aligned materials, then you end up getting, getting different views there as well. So in this case, this is the pore space. And you can see the aligned chord distribution for Y, which is in purple, is very different to the X and Z distributions. The Z distribution is very similar to the X distribution, which means that a lot of fibers in X are aligned almost sort of, into the camera, as it were. Perpendicular to the camera, so you get the thickness of the fiber. Sorry, this is pores, of course, but same thing holds for the pores. This is the fiber data. As I say, you get the same sort of thing. You get the X and Z directions being quite similar because of the alignment in Y. And because of the alignment in the Y direction, we get a sort of flat peak down here, meaning that there are lots of quite longer fibers in that direction. So it's quite a neat way to sort of to try and characterize a lot of these fibers. Again, we can look at the permeability. And so, yeah, so if you look at this sort of large fiber in this sample here, this heterogeneity, you get a very sort of a very low flow in this direction, and you get a very high flow in the other direction. So you end up with a very different sort of deviation from the average permeability depending on the direction you're looking at. It's also the case for a different volume taken of that same sample. It doesn't have the large fiber, but it still is the case. You can see the consistent material is much more consistent, as you might expect, in terms of the permeability in different directions. And then the aligned material then has a sort of a much lower permeability in the Y direction. And this is quite handy for flow batteries because you can obviously flow in a particular direction and have a low pressure drop in that direction, which is good for the performance of the batteries. You can also then model diffusion and advection as well, modeling the mass transport, and modeling in this case at various different current densities or reaction rates. So often when you're measuring mass transport in devices such as flow batteries, you have to operate in this limiting current condition because until you do, you have a mixture of kinetics and mass transport issues. So if you operate at a very high current density, then you're limited by the mass transport, and therefore you can actually measure the mass transport properly. But that's quite unrealistic for a lot of flow battery systems, and of course it only gives you sort of one data point, and yeah, it means that you can't determine the mass transport systems with low Reynolds numbers, for example. But with simulation and modeling, of course, you can simulate a great variety of different parameters. And so, yeah, you sort of, you sort of turn on the reaction, as it were, and then you see which areas of the electrode are reacting most quickly and where the diffusion and the advection is highest. And so in this case, we took some sort of sub-volume through the sample. You get these cool streamlines where you look at the concentration of the electrolyte, which is obviously related to the extent of reaction that's happened there. Not surprisingly, you get more reaction closer to the fibers, but this can sort of be really useful to look at, as I say, this channeling effect or stagnation effect within the flow batteries, which is quite a cool technique. Actually, even though you want a higher permeability in your materials most of the time, low permeability actually increases the mass transport. So you can think of it as sort of agitating the solution a little bit, I guess. I realize I've only got 15 minutes left and I'll leave some time for questions. So I'll leave the modeling side of that and just quickly go over ways in which we're moving on to using electrospun materials in different ways. The first of which is to change the polymer. So instead of using this polyacrylonitrile, using lignin, which is a bio-derived sort of a waste product as well of the paper industry. And this is something that Anna's group in Queen Mary and Magda's group as well, obviously talked a lot about this in the STFC talk, used quite extensively. We use this for flow batteries in a recent paper. I won't go over the details because I'm running low on time, but the lignin has sort of a higher concentration of surface functional groups, particularly oxide groups, which would be quite handy for the performance of the battery in terms of the electrochemical activity. You can see the reversibility is a little bit better here. We also tried to dope these materials with phosphorus, which has been shown to sort of improve the performance of carbon materials in other systems sometimes, but we found it actually degraded the performance in our materials, and we think this might be because of a sort of steric blocking effect of changing the absorption ability of the vanadium onto the fibers. But we need a bit of further research and possibly some modeling to look at that. You can see for the sort of normal GDL paper, it actually improved things quite a bit. As I should say, the phosphorus doping is in the dots there. And so we tested it in a flow battery as well. Though we get good activity with these materials because they're higher surface area, this is a sort of static test, a cyclic voltammetry test. And so when you actually put it into a flow battery, you've got to take into account all of the flow characteristics stuff I was talking about in the modeling section there. So permeability and homogeneous flow, etc., etc. And so actually the electrospun materials end up being slightly worse performing in the battery. But of course, they're highly unoptimized at the moment. There's lots of things we can do to optimize the microstructure as well as the surface performance. And yeah, so I think as a start, it's pretty good. It's quite comparative performance. We also did it in full cell testing, which it's not loading for some reason. So I think for some reason this image is massive and it often freezes things. Okay, I'll skip that then just in case it crashes everything. And it's going to take a while to skip it as well. So yeah, so we cycled the battery as well. You end up with sort of quite low Coulombic efficiencies, often in flow batteries. As I say, you've got these side reactions, and that could be a problem over time and something that really needs to be sorted out to improve these things. Obviously, electrospun fibers being high in surface area are really useful for supercapacitors, and this is some work from Magda's group by Philip Schlee and Servan Eru into supercap materials. They've actually also sort of put in the spin dope in the solution that they're electrospinning, put some sodium nitrate, which massively increased the capacitance, which is really great. And also with a bit of alkaline treatment as well in the carbonization step, you can introduce this sort of microporosity onto the fibers themselves and increase the performance of the supercap. So there, yeah, surface area and surface properties are really important there for the supercapacitors. I will probably skip over this a bit quickly. This is just something that, some context, some work from Paddy Cullen and Gen, where they're using charged graphene sheets in solution to deposit platinum nanoparticles for fuel cells on the electrodes. Paddy developed this process a little while back, and we realized we could use it as a reducing agent for platinum precursors in fuel cells. And you get this really nice distribution of small particles across large areas of these graphene sheets. And so you get quite good performance in the fuel cell, and you get incredible durability, which is the most important thing, which was looked at with identical location TEM as well. Often these particles will agglomerate as they degrade in the fuel cells, and so we can use identical location TEM to see how that happens. Anyway, all that to say that this method provides a really nice distribution of particles across the surface, and the particles are sort of well adhered to the surface of the graphene as well, giving good long duration performance. And so my PhD student, Vivian, pictured here, is trying to use this in flow batteries, trying to use that method to immobilize some bismuth nanoparticles on graphene and modify the felt fibers in that way to try and catalyze the reaction. Bismuth has been shown to have a positive effect in the vanadium flow batteries. It's a bit sort of up for debate as to how that happens. Often it works just in the electrolyte solution as well. She's also modifying the surface area of these felts through interesting ways. I haven't got enough time to talk about that for now, but she will be giving a talk at the UK RFB network meeting, which is virtual, obviously, on the 6th of July. So if you want to go to that, I'm sure that'll be a great talk. Vivian's done some really interesting stuff, and yeah, it'd be good to see her stuff. So 10 minutes left, I think that's probably about right. I've skipped over quite a few things, so if you've got specific questions on those, we can go into it in a bit more detail. Obviously, there's a lot of work from other people in this, particularly from Matt Koch, who's up there on the left, Paddy Cullen there. I actually did my undergrad with Paddy as well, which is great that we ended up working in sort of similar areas, and he's now got an academic position in Queen Mary as well, so I'm sure his perspective would be interesting at some point in the future, Rema, if you want to ask Paddy. I've just now dropped him in it, I guess. And Maria here, who was Anna's postdoc from a grant that Anna and I wrote together while I was still a postdoc. That was another thing, actually, getting some experience of writing grants is obviously very helpful. So ask your supervisor if you can chip in on their next grant application. They'd probably be quite grateful of that anyway. Yeah, Maria, so we got this small grant from the CAM IES, which is headed up by Claire Gray. And this gave us about a sort of 12 or 11 month postdoc in Maria, and she did lots of really good work there on the lignin fibers for flow batteries. So she hadn't done any flow battery testing before, and within a year managed to get a couple of material for a couple of papers, which is really great. She's now doing a postdoc in Magda's group in Imperial. So all of this is to say, I think that collaboration is vital. It's not only fun, but it's better for your science. You'll end up making friends that you'll bump into in science for the rest of your career and the rest of your life. For example, as I say, Matt and I both got some travel grants when postdocs to go to each other's labs. And that meant that we spent months over email, not really getting particularly far on these papers. And then we went and worked together properly and got a bunch of papers out really quickly, which was really great. That then led to Matt getting a job in our department as well, which is great. And then obviously led to me meeting Pablo, and we're collaborating as well. All of these things, sort of all these connections, I think are really great, and you should try and nurture them as much as possible. I guess that's my take-home message, so I'll stop there.
Cool. Yeah, thank you very much, Rhod. That was really, like, I really enjoyed that talk. So I guess, yeah, I'll dive into questions. We've got a question here. The person's asking, so A, how do you define your performance in a redox flow operation?
Okay, that's a good question. There's lots of different ways you can define it. As I say, there's sort of a hybrid between a battery and a fuel cell. So you can do, as in a fuel cell, you can do a polarization curve. So that is taking the voltage at lots of different current densities, and you end up with this sort of graph. Oh, it's going to freeze on that slide again, isn't it? 1 second. Okay, well, you end up with the polar curve essentially. So for that, though, you need obviously you need a consistent concentration, and so you need to do it. You need to sort of recharge the battery in between to get that polarization curve. While I'm stuck on this dodgy slide, that's the other way of testing it, is actually looking at the cycling performance between fully charged and fully discharged. So this is an example of a polarization curve. So we're doing different current densities and looking at the cell voltage. That's looking at things like the overpotentials that arise from the charge transfer reactions, but also mass transport and things like that. So in an operating fuel cell, that all comes into it. In an operating flow battery, I should say. And then to do that properly, depending on how long your measurements take and how big your tanks are, you might obviously deplete your electrolyte, which then changes the reversible potential of your system. So this is measuring the overpotential away from reversible potential. Obviously, if you change the reversible potential, you have to account for that as well. So that's one way of doing it, and that says, we've got fewer voltage losses at a higher current density, therefore the performance is better. And then I won't go back onto that slide because it takes so long to move on from it. But if you do charge-discharge curves, you can then look at things like voltage efficiencies and coulombic efficiencies as well, which are quite important for obviously a system like a flow battery system becomes economical after it's installed for many years. So the idea is that hopefully the degradation of these materials is a lot lower than in lithium-ion batteries, for example. And so you could install a flow battery and have it there for decades working well. Obviously, if you've got anything below a very, very high coulombic efficiency, then your capacity is going to fade during that time. So one of the reasons why, I mean, obviously you can just change your electrolyte, which is quite handy. You can just pump out old electrolyte and put new electrolyte in, which is quite good. And in the case of the all vanadium flow battery, you can regenerate that electrochemically without having to do any sort of chemical separation. So there's definitely ways around the low coulombic efficiency, but it's not perfect yet. So
yes, so we go with the next question. In a non-limiting current environment, do you find diffusion has any correlation with performance?
Yeah, it will have some, but as you can see from this polar curve, actually on this, often at operating current densities for flow batteries, you don't see too much mass transport issues actually. Although there will be a sort of, there'll be a very quick drop off often with flow batteries. And also I should say that this is taken at a fully charged state. Of course, as you get towards the lower states of charge, you have less reactant effectively, a lower proportion of reactant in your electrolyte, and so that becomes much more important. So at lower states of charge, you get a very sort of, you get the mass transport issues coming in quite earlier. So there's some effect, but largely it's when you approach that limiting case that it's really important. Of course, if you have worse diffusion or worse advection of your material, then you're going to reach that point a lot quicker. So basically, you want to be at the point where the diffusion isn't an issue for as high a current density as you can.
And sort of following on from that question, is there a direct relationship between the Reynolds number, Sherwood numbers, permeability of your battery and battery performance?
There's a direct relationship with all of those numbers and the permeability, and then I would say, I don't know about a direct relationship between the performance of that, between that and the performance of the battery, but there is obviously an influence. As I say, you could look at the permeability of the different parts of the electrode, and unless you do some flow modeling, like in the case of this lattice Boltzmann modeling, you would think, okay, I've got good permeability throughout the electrode. you sort of perhaps miss this channeling effect. And so that can have a real effect on the performance of the local performance of the battery. So in that way, it wouldn't be a direct relationship, I guess, right? Because you'd have some overall permeability of that material, but you might have a worse performance than that would otherwise suggest, because you've got these heterogeneities in the material, if that makes sense. So all of those things are directly related to the permeability, but then the permeability doesn't necessarily directly marry up with the performance of the battery based on the microstructure. So these things are slightly more complicated than that.
Well, I guess, yeah, I have a question. So what do you think are, the main advantages or disadvantages compared to lithium ion? And, looking at the future of redox flow batteries, what still needs to be done, or, to make it actually, commercially?
Yeah, that's a really good point. I mean, there's obviously quite a few differences. As I say, the advantages are things I talked about at the beginning, like the decoupling of the energy and the power, the wide range of different chemistries that you can use, the flexibility of the system, there's no intercalation reactions going on here, it's just surface charge transfer. So in theory, your system should be very robust, in the same way that a supercapacitor is more robust than a battery, for example. The problems are the energy and power densities are very low, and so you have to build quite a big flow battery to make it suitable, and therefore you've got this big capital cost. That also obviously means that you can never use it for a portable application. But they definitely have their place, and I think that obviously you see a lot of lithium ion being used in stationary storage now, and I think that's largely a sort of byproduct of the cheapness and availability of lithium ion batteries, and the fact that they work really well at the moment, right? They're really well developed. Prices come down hugely, and so they're an option for large scale storage. Probably not the best option for a variety of reasons, and degradation being one of the big ones. Flow batteries issue at the moment is cost, probably, and reliability of some of the more nascent technologies. The way that things seem to be going, I haven't mentioned at all organic RFBs here, but this is a big area of research using organic molecules as the redox couples. That can give you all sorts of advantages. You can go to higher voltage systems then if you're using organic electrolytes as well, away from aqueous electrolytes, and start to increase the energy density of these systems. You can also then tailor the organic molecules. So, for example, you could put a long chain to hinder the crossover between the positive and the negative electrode. So there's a lot of tweaking of the chemistry you could do there. I think in terms of aqueous flow batteries, things are probably moving a bit towards zinc because of the price of vanadium in the last few years. Well, it's always been quite high, but it's gone up a lot as well. So I think these systems need to be quite cost effective, basically, for people to adopt them. However, I would say you have to look at the cost over the whole lifetime of the thing, and perhaps it's a bit short-sighted to just look at the cost per kilowatt hour or whatever. But I think that there needs to be a lot more focus on grid scale storage in general. I think flow batteries are quite a cool system within that, but grid scale storage is really key. There's a lot of focus on automotive storage, obviously, at the moment with the Faraday Institution, and that's great. That's really, really key. But we also need to decarbonize our home electricity and our industry and all of this kind of stuff. And for that, we need to have 100% renewables on the grid, and for that, we need effective storage. So storage is really key.
Cool, thank you. Pablo, do you have any?
Yeah, I would like to ask about organic molecules. I don't know, what are the main challenges there? The durability, the stability. I know.
Yeah, so stability is definitely one of the main challenges. Electrolytes also as well. Electrolyte choice. Often a lot of these all of these organic molecules will be low, only soluble in certain solvents, and not particularly highly soluble either. So you often have to use either expensive or flammable electrolytes. Sometimes that can come with the advantage of increasing the voltage window, though, and therefore the power. But yeah, I would say stability and ability to produce large quantities of the materials cheaply, I suppose, is probably the disadvantage with them. And the advantage is, say, you get really whiz organic chemists to build all of these really bespoke molecules that have, great charge transfer, but also low crossover and good good wettability on the surface of the electrode. You can also introduce things like redox mediators into there, I guess, which could be quite cool. Yeah, so I think that's a really interesting area of science, and one in which I'm sort of, I mean, I think organic chemistry was by far my least favorite topic at undergrad, so I'm looking to collaborate with organic chemists on this sort of area rather than get my hands dirty myself in that sense.
Thank you.
I've got a quick question. Earlier on in the slide, you showed some really, really detailed images of some carbon fibers. Some really, really nice, like, nano CT images. Just wondered, did you have any challenges kind of putting those together? Because
these ones?
Yeah, because in lithium ion, when you try and image carbon, it's quite difficult because of the low X-ray attenuation.
Yeah, so this is the sort of culmination of lots of trial and error, I think. If I was doing this now in the group with the demand on this machine, I probably wouldn't have got here because I wouldn't have had so many scans that would sort of have failed before getting to this point. So actually, yeah, producing these images of these small fibers is quite tricky. Phase contrast is vital. You can see you get that. And actually, if you sort of, it just happens that the fiber size in this case is kind of nicely tuned to the phase contrast, so that you get most of the fiber is sort of filled in, as it were, by that phase enhancement contrast. Look at the larger fiber over, sorry, my mouse, over there. You can see that the contrast between that and the void is much lower, right? So there are all sorts of segmentation tools you can use to help with that, like watershed segmentation work best. But for me, I found that actually these samples were done laser lathing a column. So obviously you don't want much material outside of the field of view because that gives you a lot more noise as well, so you get worse contrast. But I found in the end the best thing to do, because this could sometimes delaminate the materials or burn the edges of them. So in the end I just cut a point with a scalpel and just sort of scanned the point. So yeah, it took a lot of I think then with lithium ion batteries it's also tricky. You have much more dense electrodes then as well. So these are sort of 80 to 95% porous materials, so not particularly dense, and so alignment is quite difficult as well. It's a work in progress.
Thank you, Rhod. I think I'll just ask one last question because I think time's up. So I think, like, given your career, what do you think like the defining point was that set you on this path? And any last words of advice to any young researchers that
Yeah, as I say, it was sort of, there's a lot of events that come together. I mean, if you believe in fate, I guess, you sort of see lots of these points in your life where you kind of branch off into other places. I don't believe in that, but there's lots of points where things could have gone differently, right? I could have done my PhD in a different group. Dan could have not called me because he was busy, or whatever. I could have chosen to go to Cardiff instead of Oxford. These things would have all changed all of these decisions. And that's sort of why I said, I guess, like, it's great to have a plan, obviously, but I think if you're too set on that plan, you're just going to get disappointed when something goes differently. However, I would also say, I say I've been quite lucky in the way things have panned out. I've worked hard, and I think I guess the main thing was that when I found something interesting, I followed that route. So I should say my PhD actually started on some different project, and some other opportunity came up that I thought was more interesting. And instead of just carrying on with what I've been told to do, I said, I want to do this, I want it's better. Obviously, Dan's very open to that sort of stuff. So I think you should follow what you're interested in and work hard, and, as I say, collaborate and diversify your, both your science and your extracurricular activities. And that stood me in pretty good stead. But then it's so random as well. It's a very competitive thing going into academia, and I've seen lots and lots of people who are excellent really struggle to get these things, and I've been very lucky to get a job in a place that I really enjoy working. So I wouldn't say it's particularly good blueprint necessarily. I mean, but yeah, hopefully it's of interest.
All right. Thank you so much. I think that brings us to the end of our webinar. It was really enjoyable, and thank you, Pablo and Hamish, for joining in. It was really good. Thanks, Rhod.
Yeah.
And stay tuned,
Thanks,
everyone. We'll send you an email.
For the opportunity. Cheers. Bye.
Cheers.
Hey,
Bye-bye.
cheers.